When you learn substitution in Calc 1, they teach you U substitution, right? So you use a little U of x, which is an inner function, right? So U sub, and of course it doesn't have to be U sub. They just, teach it to you that way. U substitution means that you're going to use U of x, which is an inner function within the integrand. But the trick of it is that it's not the only option. It's just taught to you like that. That's not the only way that you can do types of substitution. And we're going to learn a different one right now. We're going to learn trigonometric substitutions. Now, trigonometric substitutions are really interesting because what you're going to do is you're going to take an algebraic expression that's in terms of x, and you're going to rewrite it into a trigonometric expression in terms of theta. And it will work, right? So rather than using a u of x, you're going to do a completely different kind of substitution. But what'll happen is it'll make things in the integrand easier in the long run. Now, I'm not going to tell you this technique is easy, but it works, and it's kind of amazing. And the reason it works is because of your favorite and mine, the Pythagorean identities. They're everybody's favorite. Everybody loves them. Can't get enough of them. Right? The Pythagorean identities are the reason this is going to work. All right, so let's start. There are three main types of trigonometric substitutions that we make. So if your integral contains something like a squared minus x squared, you would do this substitution. So this column over here is that type. And you can see that's an algebraic expression. It involves an x. And the substitution you'll make is that the sine of theta is equal to x over a. In other words, x is equal to, well, if you solved this formula right here, if you take it and you solve it for x, you would have x is equal to a sine of theta. Dx, which is the derivative of that, would be a cosine of theta, and then of course d theta to get you your differential. And theta would be the arcsine, right? So if you wanted to solve this for theta, theta is the arcsine of x over a. Matter of fact, it's easier if you see right up here. Right? If sine of theta is x over a, then theta is the arcsine of x over a. Now, you don't have to memorize all three of these pieces. All you need to know is that a squared minus x squared leads to this substitution. If you have this substitution, you can build the triangle and find all these values for it. And the only restriction that you have is that theta would have to be between negative pi over 2 and pi over 2, and that's because that's a restriction on arcsine. Arcsine of theta has those same domain restrictions. All right, now before I go anywhere else, let's look at that triangle. Here's your angle theta, and the sine is the opposite over the hypotenuse. So you can see sine is opposite. Here's the hypotenuse, and you can build this triangle and you can use it to find other pieces that you need. Right? So if you know that your integral contains a squared minus x squared, you will use this substitution and this triangle. Everything else will fall out of that, or happen because of it. All right, now what about the second one in the middle? The second one is when your integral involves a squared plus x squared or x squared plus a squared, one of those two. In that case, you will use the substitution, because of course they're equivalent, of the tangent of theta is equal to x over a. Tangent, of course, is opposite over adjacent. So if you know this, if you know tangent of theta is x over a, you can build the triangle. This is happening because of the Pythagorean identity. I should have said that was happening here as well, right? Because of the Pythagorean theorem, right? A squared plus x squared is equal to the hypotenuse squared. So if you solved it for the hypotenuse, you'd have this, right? And same thing is happening over here on this triangle. Now, x would be a tangent of theta. Dx would be the derivative of that, which would be a secant squared of theta d theta. And therefore, theta is the arctangent of x over a. And arctangent actually has the same domain restrictions. So arctangent has to be right here. Right, that's the same domain for arcsine and arctangent. All right, last but not least, the third type. In some ways, the most tricky type, not because it's particularly hard, but it uses a form that we're not as familiar with, we're not as comfortable with. It uses that the secant of theta is x over a. Another way to put that would be that the cosine of theta is a over x. That would be another way to say the same thing, right? Because cosine and secant are reciprocals of each other. So the secant is the hypotenuse over the adjacent, right? In other words, cosine is adjacent over hypotenuse. So you can build this triangle. So here's the adjacent, here's the hypotenuse. And you can build it from either way that you want to think about it. All right, so if x is equal to, if secant of theta is equal to x over a, then x is equal to a secant of theta. Or if you want to use this version, then x, you multiply by x, you divide by cosine, and you'd have a divided by the cosine of theta, because of course secant is 1 over cosine. Dx is the derivative of secant, which is a secant theta tangent theta. It's just easier to do it that way than to try to do some kind of quotient rule or something like that. And then theta would be the arcsecant of x over a. And again, it might be easier to think of it as the arc cosine of a over x. And that domain restriction is right here. All right, so now let's put it into practice and see if this makes any kind of sense whatsoever. And it does, it really does. It works out, it's great.